Welcome to this video lecture. We are going to introduce, in this video lecture, doing process control in Simulink. I'm going to start introducing the proportional integral derivative, or PID controller. So I'm going to do this in pieces, and today we're going to talk mostly about proportional control and how that aspect of a PID controller works. We're going to go back to our car and cruise control example. In the last lecture, I talked about what it means to be closed loop, and we talked about this cruise controller, or this computer/computer algorithm that is figuring out, based on my velocity, how do I need to adjust my fuel valve position. So we're actually going to break this controller down, just thinking about it as an algorithm. And it's actually, to do a proportional controller, it's actually very simple. So what we would do, of course, to control something, you need to be able to measure it. So we have our speedometer or our velocity transmitter. So this is just the sensor that is telling us how fast we are actually going. We would need to tell our car how fast do we want to go. So the speedometer tells us how fast we're actually going, but then we would need to enter our set point. So our set point comes in, which is basically our desired velocity. We would calculate the error between our desired velocity and our actual velocity. So actual is measured by the speedometer, and desired is something that we would enter into our car's computer, usually just with some simple controls on the steering wheel. So this block is an adder, or it takes the summation or the difference between two different signals. So in this case, we would take our desired velocity and subtract off the actual velocity. That would give us this error calculation. So that's what this signal would be, is the error between our set point and the actual measured velocity. So to do proportional only control, we could basically take that error, which would have units in this example of miles per hour, and we could say, okay, depending on the miles per hour that our car is going, we want to change our fuel flow rate to with a certain number of gallons per hour. So we would take this error signal and we would just multiply that by a gain, a process gain. So in Simulink, that process gain block looks like a triangle, but basically you take the signal coming in, multiply it by a number, and then it spits out an output. So the proportional control algorithm looks like this. The value that our manipulated variable takes on is equal to some constant, this k sub p. This is called our proportional controller gain. So that's where this sub p comes in. So this is our proportional gain for our controller. This is what we're going to call a tuning parameter. This is something that we would set so that we see the desired outcome coming from our controller. So that kp would show up here. So we would take our error signal, multiply that by some proportional controller gain, and that's going to give us the value that we set our fuel flow rate at. So I'm going to pull up our example in Simulink again. So remember, we just used this simple transfer function model to represent our car. In this case, our model is this: we give it a specific fuel flow rate, and then our car model is going to spit out a velocity. So the way to implement proportional control would be, first we need to take our signal and feed that into that summation or difference block. So I could go to my library browser, go to operations. This block would do the trick. There is another one in here that I like a little bit better, this summation block here. So I'll drag and drop that over. I can tell this block what signs I want. I'm going to do that later. First, I'm going to go here, right click on the block, go to Format, and then flip it. And you'll see why here in a second. So I want to take in this line here would represent my sensor, or my speedometer. So this is where I'm actually measuring the velocity. That would come into my summation block, and if you remember, I want that block to be that input to be a minus. Oh, and I did that wrong. So if I double click on here, this lets me put my signs in, so I want this block to have first a minus and then a plus. So basically it's going to take whatever signal comes in here. This is where I'm going to put my set point, it adds that, and then it subtracts off the actual. So I'm going to steal this step change for now, and I'm going to call this block my velocity set point. So I will connect that here. And let's say I know this is a step block. I'm just going to say I want to have a velocity of 65 miles per hour. I just want to go the speed limit on a normal highway. So even though this is a step block, my initial value and final value are the same. So this results in being just a constant. Okay, I want to add in my controller here. So in my library browser, I'm still in this math operations, and I can find a gain block here. So I will drag my gain over. I'm going to first flip it. I'm going to take this error signal. So remember, this summation block is now calculating the error between my set point and my actual velocity. Here, this is going to be basically my proportional controller. And actually, what this block is going to spit out will really be my fuel flow rate. You'll see why I'm doing this here in a second. So this is still my controller. I'm giving it this name of fuel flow because this is going to show up in my plot later. So now I have the ability to go closed loop, which means I can have my controller tell me what my fuel flow rate should be. So I would no longer need to manually input my fuel flow rate. Or in the case of driving, I would no longer need to manually press the gas pedal. The cruise control is going to take that over for me. So I can go closed loop and tell my car, hey, I want you to tell me how fast or how much to push the gas pedal or how much to open this fuel flow valve. So I've gone fully closed loop here now. So I need to tinker around with this proportional gain. So remember, coming into this block is a signal. It's the error in my velocity as measured in miles per hour. So this fuel flow gain value, my K sub P, is what goes here. This is going to have units of gallons per hour divided by miles per hour. So this is saying, depending on what my error is, I want to have this many gallons per hour coming in. So let's say we're off by, let's say our set point 65, let's say we're going 35 miles per hour at any given time. So if we're only going 35, my error would be 30 miles per hour. So I might want to add in, for every 30 miles per hour, I might want to change my fuel flow rate to be 3 gallons per hour. So I'm going to have a gain of 0.1 here. All right, so let's just see how this works with kind of a not very aggressive controller. I've run my simulation, and I can now look at how I'm doing. So what you'll notice is that my velocity gets up to a little over 50. So we're not actually hitting our set point. It's useful to add in, if I click on my scope, I can go to this number of input ports and I can change this to 2. So it's also useful to grab your set point and to plot your set point and your actual on the same plot. So I'll just run again. My simulation is running for 100 seconds. So we'll notice that we don't actually hit our set point. So we do notice also that our controller does get us close to our set point, and it has a fuel flow rate that looks like this. So what we can see, I'm trying to get these on the same plot. So actually, let's go back to the presentation. All right, so these are how the results might look. This is with a different controller gain. So one of the problems with a proportional controller is that our signal here, with our manipulated variable being proportional to this error, if we ever actually get our error to be 0, meaning that we're hitting the set point, well, that means that the only way to hit that is if you have an MV of 0. So one of the pitfalls of a proportional only controller is that it can never actually reach your set point, and that's because to have a finite value here for the value of your manipulated variable, you have to have some kind of finite error to power that. So one way that we can close the gap here and get closer to our set point is we can increase the value of this controller gain. So let's do that. So if I go here, I can tune my controller, and let's say I want to be much more aggressive and I want to get closer to my set point. So I can give this a gain of 0.5. So here I'm going to run, and you'll notice that I do get closer. Now I'm over 60 miles an hour. So I'm over 60 miles an hour, but I'm still not to my actual set point of 65. And so for a proportional only controller, we'll never really get to our set point because it relies on a finite error to give you that value of the MV. The downside of being more aggressive in our tuning is that we're going to get a lot more aggressive with our MV. So in this particular case, at the initial stages when we have that high error, we end up with a fuel flow rate, or a desired fuel flow rate, of like 32.5 gallons per hour. So our valve may not actually even be able to handle that. Probably not. This would be like crazy acceleration. So there's this trade-off between how close you want to get to your set point with a very aggressive controller gain, and then the impacts that might have on your car. This may introduce safety issues, or really, just practically speaking, just would push the car beyond its physical abilities. So the way that this is handled in control is by adding different types of controller action. So as you can see, in this particular case, we do have this persistent error here. So if we could do something like integrate that error over time, that introduces another control mechanism, which will be integral control action. So stay tuned for the next video where we'll add in integral control action and see the effects there.